Okay, welcome back, everyone. So now we will move swiftly onto part 4, and this is a very short one, and it introduces, even though it's very short, it introduces one of the very main topic or very main concept in physics called momentum. And this concept is so central to physics. Physics or science in general is a subject that is a field that is constantly evolving, right? So when you make new discoveries, you realize some of the old concepts are obsolete, and you update them, and that's why it's a subject that's sort of constantly getting closer and closer to the truth, constantly refining and getting better and better results, right? But momentum is one that has been tested and sort of weathered and sustained through all the tests and experiments and criticisms and theoretical development. Momentum is still a concept that is so central, and we now understand it is a concept that is very fundamental to how the universe works. Really, it's about due to it's a quantity that sort of it manifests itself due to the symmetry of the universe. Okay, so it's something very fundamental. We won't get that deep in our lesson, but we will just focus on its practical application, which is really, that's why I call it the theory of collisions. Okay, so far, almost rarely there are things colliding. At most, there's something contact, there's a contact force pushing on something requiring to accelerate an object. But yeah, there's rarely two objects sort of colliding, right? If I throw a projectile, I'm not having that collide with something else. And obviously, if I have a bottle of gas, all the air particles are constantly colliding to each other, right? If I have just a tank of gas, and that collision will create temperature and pressure, which you will learn all about in 3B as well. Yeah, there's plenty of applications, but we'll start with seeing how do we calculate this, and it introduces a new law, a new conservation law, and it's called the conservation of momentum. So momentum is a new concept. It is like energy. It is a concept that is conserved. So put that very simply is if you have a system and you start off, you just tabulate all the initial, you realize it's a very similar skill. It repeats itself over and over again. This time we tabulate all the momentum at the initial state, and you tabulate all the, you sort of find out and summarize all the final momentum. You calculate, add up everything, and they should match. Okay, if there's some unknowns in this process, for example, if there's a final velocity that you don't know, by equating the initial and final state, we will realize that you can now calculate and predict what will happen to some of the unknown variables. So a very useful idea. It is a vector. It is a new vector concept. So we'll talk about that. We'll give the definition. But before we jump into the law of conservation of momentum, we will actually upgrade our Newton's second law. Okay, there's something wrong with it. I'll talk about that in a second, and finally we'll conclude that with looking at how we actually apply this. Okay, so this is the agenda. Okay, so let's start with definition. Okay, so I'll motivate that with the improved Newton's second law. So what's wrong with Newton's second law? Well, it looks pretty well, right? As far as we understand it, we state it as, right? So in one dimension, we kind of say it like this. And just to iterate this over and over again, I like to write it in this way, not F equals MA, but MA equals F net. Number one, I'm putting MA on the left-hand side because what is our goal? Our goal is really to find the position function of something, to find out at every single time where is the object's position, right? The suvat is the change in position, for displacement. All of those is our goal is to find out this, not this. Force is the tool to find out that. So the thing that you want to solve for, usually in math, you put it in the left. It's just, it rolls off the tongue. It's more catchy to say F equals MA. However, this is more intuitive in terms of, or more correct in terms of what you're going to use this for. It's not just a textbook academic exercise of giving you M finding F, giving you F finding A. It's not that, right? We have a goal in our journey is we want to figure out how things move, and A is sort of the issue we're looking for. Secondly is net, F net. So if I just apply a force on something, it doesn't necessarily give an acceleration. It's the net force that will give, right? If I apply the force on this way, it does not necessarily accelerate to that way, because if someone else is pushing that way, and if they push it harder, it will be accelerating this way. So the fact that I apply a force to the left does not necessarily will move to the left. It does not necessarily mean it'll accelerate, right? It's the net force that will cause the acceleration. Okay. So if we have the idea is, if you want to find the acceleration, you need to add up everything first before you find out which way it's accelerating. Okay. And this is of course one dimension. We need to upgrade that to 2 dimension. All right. So or 3 dimension in general. So now you need to worry about the components. If you're doing an algebraic view or geometric view, you need to calculate the magnitude and direction separately. Okay. Now, here's the problem is, what if I apply a force on something that doesn't have a mass? Okay, so what doesn't have a mass? Photons are one object, right? Photons are not, is a concept obviously that's not invented in Newton's time, but now we know there are some objects, some particles that do not have mass. Photons are particles of light, okay? So back in Newton's time, the prevailing theory, Newton thought light was a particle, but it was finally kind of figured out it didn't work quite well, and Huygens, a European physicist, sort of thought proposed that light is a wave, and that works much better. Okay. However, when it comes back to Einstein, a couple 150 years later on, we realized that actually Newton wasn't so wrong after all. Actually, light is neither a particle nor a wave, right? This is you will learn about this in 3C. But sometimes it behaves like particles, sometimes it behaves like wave. When it behaves like particle, it behaves like a particle without mass. Okay. Now that's weird, because if you have no mass, then lights can actually exert a force on something. How can you exert a force when something has no mass? So there's something missing when you look at that picture, right? So I've thrown a lot of information to you about like photons, which is the particle of light, the concept of light being a wave, the concept of light being a particle, and the concept of the modern concept of light is neither a wave nor a particle. Both are good models of it, but it's really its own thing, which sometimes has a wave particle, sometimes have a wave behavior, sometimes a particle behavior. Those those are really exciting modern ideas you will learn in 3C. We won't get there yet in this course, but yeah, so don't worry about the reasoning for that yet, but just understand this. Sometimes, yeah, sometimes things don't have mass. Another case where this will not work is, what if the mass changes? Here's another example, right? So if I have a conveyor belt, right? So, and I have some sand over here, okay? What's the force required to move the conveyor belt at a constant velocity, right? Well, constant velocity, assuming no friction. So I have sand on a conveyor belt, right? It's gonna move the sand over here into a bucket or whatever, right? Yes, if there's friction, I need force to overcome that. But if there's no friction, then it's sort of free of charge to move it at constant speed. Okay, constant. However, if I keep adding more sand onto this, like with a funnel, right? And now this will get more and more massive. The mass will increase. Okay. Is it still for free that it will go at constant speed? Or do I actually, if I start increasing the mass, do I actually need a force to start moving it? Now, it's hard to think without friction, but just think in space. An object, okay, let's say it's moving it, let's have a bucket of sand moving in space, a bucket of sand moving, just floating in space and moving at constant velocity somewhere. Now I keep adding more and more sand into it. Now it increased the mass of this. Now it seems like in order to maintain a constant velocity, not even accelerate, you may need to sort of exert some extra force to push it to do that, because what is mass again? Mass is inertia, right? It's a measure of inertia. It's telling how much it doesn't like to move, and if you increase that, you will have a hard time maintaining a constant velocity. Okay, so all that sort of suggests we need sort of an upgrade to especially this side of things. When you apply a force to something, it looks like the mass itself needs to be part of the variable, part of the equation as well. Okay, and that leads us to the definition of momentum.